Hey Algebra, let's work through lesson 15 in Unit 6. We're going to talk about the vertex form. As a tiny little review, we've already talked about standard form, which is ax squared plus bx plus c, and factored form, which is either x times a parenthesis or x plus or minus a number, x plus or minus a number. Okay, so today, vertex form. First of all, notice and wonder. Two sets of equations. It's our warm-up. Student task statement says, what do you notice? What do you wonder? Look at set 1. Look at set 2. What do you notice? What do you wonder? Okay. In set 1, I notice that f of x is missing a constant. Okay, that's standard form without a constant. G of x is also missing a constant. It's factored form, but there is no c term. And then h of x, that's a strange formula that we haven't seen things like that yet. Like this right here looks new to me. I have a binomial squared, which remember we talked last lesson is really that. And then a minus 4. So it almost looks like I have two constants that would have to be sort of combined. But in fact, gosh, if I square that, I get x squared plus 4x plus 4 minus 4. My constant is gone. That's so interesting. So no constant. Wow, I wonder. Yeah, these are all the same. So h of x simplifies to this in standard form. G of x is also that in standard form. And f of x is already in standard form. So they are all the same equation. Oh, let's look at set 2. Wow, I think those are the same too. Okay, I'm going to FOIL this after I flip that order because that's really annoying to me. So first term times first term, outer, inner, 5x, and last, I get negative x squared plus 6x minus 5. Yep, it's the same. So I'm going to assume that that one is also the same, but I'm not going to work through the work. Okay, even though this says 4, it's all going to work out to give me a minus 5 at the end. All right, so actually what we see here is this is standard form, this is factored form, and this right here is actually vertex form. Standard form, factored form, vertex form. Cool. All right, so the new information we're doing today. Here are two sets of equations for quadratic functions you saw earlier. In each set, the expressions that define the output are equivalent. So everything is equal. F of x, g of x, and h of x all give you the same output. They are all equivalent equations. The expression that defines h is written in vertex form. We can show that this is equivalent to the expression defining f by expanding the expression, which I did in the last slide. Because, as usual, Miss Carly does not look ahead to see what's going on, and I get ahead of myself sometimes. So if I expand that, I get standard form. Okay? Question number 1 says, show that the expressions defining r and p are equivalent. Luckily, I did not expand r in the previous slide, but I need to, I copied this onto a new slide so that I had room to work. All right, so number 1 said, show that the expressions defining r and p are equivalent. So I need to expand this. So I'm going to write that negative 1, and then I need to write x minus 3 twice. And I'm going to go ahead and FOIL this one. First, outer, inner, last. So first times first is x squared. Outer is x times negative 3. Inner is x times negative 3. and last is plus 9. Collect like terms. I have negative 3x, negative 3x. If I add those together, I get negative 6x. Distribute that negative 1, negative x squared plus 6x minus 9 plus 4. If I combine like terms again, those are my like terms, I get minus 5. So there is expression r and p, and they are equivalent. Cool. All right, now here are graphs representing the quadratic functions. Why do you think expressions such as those defining r, h and r are said to be written in vertex form? Okay, hold on a second. I'm going to copy h over. All right, if I look at h of x, which is x plus 2 quantity squared minus 4, what do I notice and wonder about this graph? Okay, the graph of h. So if I see here, my vertex, since we're talking vertex form, this vertex is at point negative 2, comma, negative 4. I wonder about that. And then if I look at r of x, which is right here, and here's the graph of r of x. This vertex, because we are talking vertex form, I wonder if they're connected, is at 3, comma, 4. All right, so I notice this is a 2, and that's a 2, and this is a 4, and that's a 4. What's weird is this is x plus 2 quantity squared, and that's a negative 2. And this is a negative 4, and that's a negative 4, so we're good there. Okay, let's go over here. I have x minus 3 quantity squared, and that's a positive 3, and then plus 4, plus 4. Interesting. Okay, vertex form. X minus h squared plus k, where the vertex is h, comma, k. Ooh, there's something I forgot to point out. That negative 1 means I am unhappy. Negative 1 out front means I'm unhappy, which if we see it in standard form, a is negative 1, which means I'm an unhappy parabola. All right, let that sink in. That's a lot. Let's move on. Okay, so using graphing technology, graph y equals x squared. Then add different numbers to x before it's squared to see what happens. All right, so I'm going to go do that, and I'll be right back. So if we look here, move my red pen out, x squared, okay, right there. The vertex is at 0, comma 0, and it opens up, and life is grand. This is called our parent function. Cool. And then in blue, we do an x plus 4, but we moved to the left. And our vertex is now at negative 4, comma 0. And then in green, we're x minus 3, but we moved to the right. And our vertex is at 3, comma 0. So I told you guys that vertex form is x minus h squared plus k, where the vertex is h, comma k. So that h term, you can think of it as the opposite of whatever you see. This vertex is negative 4, comma 0, and this vertex is positive 3, comma 0. Notice we have not done any k's, which goes up or down. H goes left or right, k goes up or down. H is the horizontal, right? Left or right, and k is up or down. I don't know how to compare the k to up or down, but h is horizontal. All right, let's try number 2. Graph y equals x minus 1 squared, and then experiment with the changes. Okay, so I'm going to delete this graph, take some notes if you'd like to look at this before, write some things down, because I'm going to delete it, right? So here we have, I graphed x minus 1 squared first. That's in purple. And that just shifted right 1. My vertex is at 1, 0. And right there. Then I did a plus 5. And look, we went up 5. Then I did a minus 9. And we went down 9. Remember, we have x minus h quantity squared plus k. So for the first one, my vertex is just h, and my k was 0. Sorry, h, and my k was 0. And then my second one, my h term didn't change, but I went up 5. And then that third one, my h term didn't change again, but I went down 9. So my vertex is just going up and down because nothing else changed. Cool. So take a few notes, and I'm going to work on part B, all right? But I'm going to delete this, so push pause and take a few notes. So here, the colors are all messed up. I forgot to change them. We have our original function again, which just is a right 1. Our vertex is at 1, 0. For the next two, graph number 2 and 3, the blue and the black, the vertex is still at the same spot because we didn't change anything about the x minus h squared plus k. We didn't change anything at all. We changed this a in front, which I have not introduced yet. So let me write that a little bit better. Okay, our vertex form is actually a x minus h quantity squared plus k. Okay, the a term right there, just like the a term in our standard form, if it's positive, it does make a happy parabola. If it's negative, it makes a sad parabola. But also, the larger the a value, we could say the absolute value of a. The larger the absolute value of a, doesn't matter if it's positive or negative, it makes a skinnier graph. It's that vertical stretch. Okay, so the larger the a value, whether it's positive or negative, so the absolute value of a makes a skinnier graph. So if I look at graph 2, I have a 3. A equals 3. It's positive 3, which means it's a happy parabola, but it's also skinnier than graph number 1, which the a term is 1. Here the a term is 3, and we've gotten skinnier. We are stretching vertically. And then here I have a negative 2, so I flipped it over the x-axis because it's unhappy. But 2 is smaller than 3, so 2 is not going to be as skinny. The bigger the a is, the skinnier it gets. Okay? All right, so take a few notes from that so you remember how everything works. And let's move on to our last bit. All right, number 3, without graphing, predict the coordinates of the vertex of the graphs of these quadratic functions and predict whether the graph opens up or opens down. Ignore the last row until the next question. It told us to ignore something, so we're going to ignore this. And for goodness sakes, they are using different variables. Oh well. Ignore that last row for a minute, all right? Let's work on it. What we have been doing is vertex form x minus h quantity squared plus k, where my vertex is h comma k. All right, so the coordinates of this first one, I don't have a k term. I know that's opposite, and it opens up because my a is positive. Here, h comma k, and we are still opening up. Same thing, And here we're opening down because our A term is negative. Ooh, this one, I'm going to rewrite this so it looks like everything else. X minus 0 quantity squared minus 7. So I'm at 0 comma negative 7, and we're opening up. H is negative 3, negative 5. Okay, that's positive. We're opening up. Notice that that is a negative, or sorry, the A term is a fraction. So remember from our previous lessons, that's actually going to have a wider parabola because we're a fraction. All right, here, negative 100, comma 50, and that means we're opening down. And we're supposed to ignore that last one for now. I'm going to check my answer key. Looks like we got them all right. Use graphing technology to check your predictions. If they are incorrect, revise them, then complete the last row of the table. I just checked the answer key, so we're good. But I would love it if you guys would take a second and verify if you feel like it, because Desmos is super easy to double check things with, okay? Here, my vertex is negative m, comma n, and A is positive, so I'm going up. Okay, I'm assuming A is positive, right? All right, that's it for today. Good job.